Welcome to this explainer. Today we're jumping right into a topic that is quietly but massively shaping the entire future of global energy. Now, we constantly hear about wind farms expanding, right? But there's this invisible hurdle keeping us from fully ditching fossil fuels, and that is the wind itself. It's entirely unpredictable. So we're going to unpack the fascinating world of wind power forecasting. We're going to demystify the complex algorithms, the artificial intelligence, and the meteorological science that engineers are actually using right now to predict the weather and keep our delicate power grids perfectly stable. 15 to 25%. That is the massive amount of fossil fuel savings that we can achieve simply by replacing basic weather guessing with highly accurate wind prediction models. You see, grid operators literally have to balance supply and demand every single second of the day. If they don't know exactly how much wind energy is coming in, well, they're forced to keep polluting coal or gas plants running on standby, just in case the wind suddenly drops. But by perfectly forecasting the wind, we can actually turn those backup fossil fuel plants off, which makes our entire grid significantly greener. Okay, let's take a quick look at our roadmap for today. First, we'll tackle the wind intermittency problem. Then, we'll look at the relationship between wind speed and power. Third, we'll explore the 4 time horizons. After that, we'll dive into AI and forecasting tools. And finally, we'll wrap up by simulating success in MATLAB. So let's jump straight into Section 1, the wind intermittency problem. I kind of want to shatter a common illusion right off the bat here. You really cannot just put up a giant turbine, connect it to the grid, and then sit back and enjoy a constant stream of free, reliable energy. It doesn't work like that. The electric grid demands absolute stability. And wind is inherently chaotic. And that chaos has massive economic stakes. We're talking up to 10%. When wind farm operators promise a certain amount of electricity to the grid and then fail to deliver because the wind suddenly died down, they get slapped with really hefty energy imbalance charges. Research shows that these simple prediction errors can cost wind farms up to 10% of their total income. Imagine losing a tenth of your revenue simply because you got the weather forecast slightly wrong. That is exactly why accurate prediction is a financial necessity for the survival of renewable energy. Which brings us to Section 2, wind speed versus power. To really understand why that economic loss happens so easily, we have to look closely at the underlying physics. It all comes down to the mathematical relationship between the air blowing through the blades and the actual electricity coming out of the generator. Now, here is the absolute aha moment of this whole topic. It's called the cubic relationship. The power generated by a wind turbine does not scale smoothly and linearly with the wind speed. Instead, power output is proportional to the cube of the wind speed. So think about what that means. If the wind speed doubles, the power output doesn't just double, it multiplies by 8. Because of this intense, nonlinear relationship, just a tiny miscalculation in how fast the wind is blowing dramatically skews how much electricity is actually generated. And this brilliantly illustrates the absolute nightmare that forecasters face every day. A meteorologist might make a really small, seemingly harmless error in predicting a gentle breeze for tomorrow morning. But because of that cubic relationship we just talked about, that tiny speed error magnifies into an explosive failure in predicting the actual power output. If grid operators act on that bad power forecast, the entire regional power grid could be left completely scrambling for electricity, or, conversely, suddenly overwhelmed by a massive surge of it. Let's move on to Section 3, the 4 time horizons. So how do engineers actually manage this? Well, forecasting isn't just one big guess about the future. Engineers strictly categorize their tools based on exactly how far ahead they need to look, mostly because different decisions require different types of foresight. Let's walk through this structured breakdown. First up, we have very short term, and that's anywhere from a few seconds to 30 minutes ahead. This is purely for immediate market clearing and regulating sudden drops in grid frequency. Next is short term, looking up to 6 hours ahead, which helps utilities decide whether to incrementally increase or decrease other power loads. Then medium term, which goes up to a full day ahead. This one is absolutely crucial for day-ahead electricity markets, ensuring operators know exactly which generators need to be online tomorrow. And finally, long term, stretches out to a week, letting managers schedule critical maintenance and commit massive reserve power units. The stability of the grid, and honestly, the stability of your own monthly utility bill, relies entirely on executing all 4 of these horizons perfectly. Let's transition into Section 4. AI and forecasting tools. To make predictions across all those different time horizons, engineers use a pretty wild toolkit of meteorological science, historical observation, and complex artificial intelligence. First, we have the persistence method, which is the absolute simplest approach. Then there's the physical approach, which uses heavy-duty supercomputers to calculate atmospheric physics. Next is the statistical approach, utilizing time series models like ARMA or artificial neural networks. And finally, hybrid structures, which cleverly combine the brute force of physics with the pattern recognition of AI to really get the best of both worlds. Okay, let's start with the first one, the persistence method, famously known in the industry as the naive predictor. It works on a hilariously simple premise. It basically assumes that whatever the wind is doing right this exact second, it will be doing the exact same thing a few minutes from now. It's essentially like trying to guess tomorrow's weather by just looking out your window right now and saying, yep, it'll probably just be exactly like this. Now, what's really interesting here is that despite how simple and, frankly, silly the naive predictor sounds, researcher Waqas Javed points out something fascinating. Unbelievably, it is actually more accurate than most of the physical and statistical methods for very short to short-term forecasts. That is the sheer irony of wind forecasting. If you are only looking 5 or 10 minutes into the future, the naive assumption that things will just stay the same actually beats multi-million-dollar supercomputers. In fact, the industry still uses it as the ultimate benchmark to this day. But when we need to look hours or days ahead, well, we have to bring out the big guns. Numeric weather prediction relies on supercomputers crunching immense models of atmospheric physics. We're talking temperature, pressure, surface roughness, the whole shebang. Because it's so computationally heavy, these models are usually only run once or twice a day, which makes them great for long-term forecasting, but way too slow for quick updates. Meanwhile, artificial neural networks apply AI instead of trying to solve physics equations. These networks hunt through massive databases of historical wind measurements to find hidden patterns. They're super flexible, they learn from their mistakes, and they are incredible for short and medium-term forecasting. So when engineers combine these two into a hybrid model, literally feeding the supercomputer's physics data right into the AI's pattern recognition, they achieve the most stunningly accurate forecast possible. Finally, let's see how this all builds together in Section 5, Simulating Success in MATLAB. Look, before any of these complex AI algorithms are trusted with our actual real-world electricity supply, engineers have to build massive digital sandboxes to test them out. A prime example of this is the MATLAB Simulink environment, as demonstrated by the Wired White engineering platform. You can actually watch the exact pipeline in action. Step 1, they input the raw weather and wind speed data into the system. Step 2, the simulation applies advanced controls, automatically adjusting the turbine's blade pitch and applying what's called maximum power point tracking. Step 3, the model generates the final simulated output, plotting the exact power, rotational speed, and blade angle that the turbine would produce in the real world under those forecasted weather conditions. So the absolutely crucial point here is that a wind turbine isn't just some passive pinwheel spinning in the breeze. It is a highly active mechanical robot. The forecasting software actually has to juggle the constantly changing turbine state, the active pitch controller physically turning the blades, the MPPT maximizing the electrical draw, and the derating control, which is what prevents the turbine from spinning totally out of control during a violent storm. The AI doesn't just have to predict the weather, it has to simultaneously predict exactly how the mechanical turbine will react to that weather. By beautifully blending the raw brute force of supercomputers with the slick pattern recognition of artificial intelligence and testing the whole thing in rigorous MATLAB environments, engineers are finally taming the intermittency of the wind. We're minimizing those massive economic errors, and we're balancing the grid second by second. So as these incredibly advanced forecasting tools master the sheer chaos of the weather, we have to ask, are we finally ready to leave fossil fuels in the past? Well, the math suggests we just might be.